Yes, sir.
Fine. So today I'm going to discuss here one important concept in your examination point of view. It's very, very important. Transport number or transference number and its determination. Here, transport number, transference number, and then some important definitions also there. Abnormal transport number, and then how it relates with mobility of ions, then how it relates with the generation of electricity. So all the things we are going to observe today. Here, transport number. Yesterday I discussed. That is a very important concept. That is also liquid junction potential. That is related to this transport number only. When liquid junction potential increases, then the transport number or mobility of ion decreases. Okay. So here, after the liquid junction potential, one of the important topic I discussed today, that is the transport number. Here, what is the transport number? Here you see the transport number. We are also called this one as transference number or Hittrof number. Hittrof is the scientist. He only found the first determination of transport number in electrolyte solution. So that's why this is also called as an Hittrof number. Yeah, it's very simple. Try to understand the concept. Okay. Here, the quantity of electricity Qi carried through a certain volume of an electrolytic solution. A quantity of electricity Qi. Already you know, electricity we are representing Q. Q ith kind of the current electricity we are going to take here. So the quantity of electricity Qi carried through a certain volume of an electrolytic solution by ions of the ith kind is proportional to the number of unit volume. Is proportional to the number of unit volume. That is, what are those that unit volume containing? So that volume containing to the concentration Ci, because this is the ith kind, in gram ions to the charge Zi carried out by each ion, and the mobility Ui, that is the velocity under unit potential gradient. So what is this Ui? Ui is the mobility. So it is equal to, it depends on the velocity under the unit potential gradient. So we are going to represent this. I am going to represent this quantity of charge, what is that electricity we are representing Qi, because this is the ith kind. This Qi involving here, or this is directly proportional to Ci Zi Ui. That is, here Qi is equal to K is the proportionality constant, Ci Zi Ui. So already you know what is that Ci? Ci is the concentration of ith kind. Zi is the charge on the ith kind. U is the mobility of the mobility ith kind. So where K is the proportionality constant, which includes the time, the total quantity of electricity, total quantity Q, the next U1 plus K C2 Z2 U2 here. Once again, K1 K C1 Z1 U1 plus K C2 Z2 U2 plus K C3 Z3 U3. So these are the kinds of ions, these many number of ions present in an electrolyte. Okay. So here common, okay, in all the this is the proportionality constant being the same in all the ions. So because of the reason, we are taking this one as a common here, K summation. Instead of this all, we are taking height kind. Height means so many number of ions, height level, number of ions present in the electrolyte, like this. The concentration of height kind, then charge height kind of charges present in the electrolyte. U is U height kind of mobility of ions present in the solution. So this generally they are representing this one. So capital Q is equal to K proportionality constant summation Ci Zi Ui. Here the proportionality constant being same for all the ions. The next here it follows what it follows. Therefore we are going to representing transport number now. Therefore that the fraction of total current carried by an ion, if the height kind is given by, so what we are going to representing now, we are representing transport number. So how you going to represent this? The transport number containing is equal to Qi, charge on the height kind of electricity on the height kind, divided by total number of charge, is equal to, what is that Qi? What we are going to derive, we are representing that Qi is equal to Ci Zi Ui divided by capital Q summation I Ci Zi Ui. So this is called, this fraction is called the transference number or transport number. We are expressing this one like this here. So no need to explain all the things. So this is only for your understanding purpose. What are the things present in the electrolyte? But we are going to explain this here. The fractions of the current carried by a given ionic species in the solution is called the transport number or Hittrof's number or transference number of the ion. Okay, so this is the general definition of transport number or transference number. In solution, the current is carried by the ions. The amount of current carried depends on the mobility of ions. Already explained that. Okay, amount of current carried by ion, that depends on that amount of current carried, that is depends on the mobility, how much it moves faster in the solution. So that is depends. Since the positive and negative ions have different mobility, they carry different amount of current. They carry different amount of current. So the amount of current is given by transport number. The amount of current, what we are generally said, the amount of current is given by transport number. So how you going to reference in this transport number? Transport number of cation is one value, one speed, one mobility. So that's why transport number of cation, we are representing cation T plus is equal to current carried by the cation divided by total current. So we are also representing like this. We are also representing T plus is equal to U plus divided by U plus plus U minus. So what are the things are there here? U plus is nothing but what? The mobility. Why? The current generated that depend on or what is that? The current carried that depends on the mobility. So that's why we are representing the current in the transport number U. U is representing mobility of ions. So T plus is equal to U plus divided by U plus plus U minus, that is total current. Total current is nothing but what? Current is sum of the positive and the negative. Okay, so that's why total current. The next here similarly we are also representing like this. Similarly transport number of anion, it is transport number of anion T minus is equal to current carried by the anion divided by total current. We are representing T minus is equal to U minus, sorry, here U minus divided by U plus plus U minus. Okay, so small correction here. Okay, transport number of anion T minus current carried by anion divided by total number of total current. So T minus is equal to U minus, anion is nothing but what? Negative. So U minus divided by U plus plus U minus. The sum of transport number of cations and anions is always 1. We know already. Okay, in liquid junction potential, and then the previous derivation, we know T plus T minus is equal to 1, and then with the help of this equation we solve some problems also in the previous class. Okay, so this is T plus transport number of positive cations plus transport number of anion is equal to 1. Next, after this representing a representation of the transport number, method to determine transport number. How you going to determine this transport number? Here, three important methods are there. Hittrof method, moving boundary method, EMF method. But in your syllabus, you given only two methods. One is Hittrof method, second one is EMF method. Okay. So now we are going to discuss Hittrof method. How we are going to calculate or determine the transport number in an electrolyte solution or electrolyte. Just you see the mechanism, how the Hittrof explained in its rule. Just you see in this Hittrof method, here any cell you take, two compartments are there. Any cell, generally you take any cell, Daniel cell or any other, if you want to determine the potentiometry, the cell is you form calomel electrode and then potential platinum electrode you dip into the solution. So that is also containing a three compartment. Anything you imagine a cell having a three different compartment. One is anode compartment, second one is cathode compartment, then middle one, the third one is middle compartment. The variations, what happened? The first, all the ions are arranged like this. The second case, it loses, it attracts towards the anode compartment. The negative ion attracts the anode compartment here. Next, the positive ion attracts the here cathode compartment. Same number of ion, it loses. Okay, it will attract, it will adhere on the surface of the anode and then cathode. Here you see third case also, it 4, here also 4 positive charges, it is adhere, it is going into the adhere on the surface of the cathode compartment. Here also, then what he explained, the following cases may now be considered in this Hittrof method. So mechanism of the transport. What is the transport? So these type of movement of mobility taking place in the solution. That's why transport means movement taking place or mobility taking place of the ion. So first one, let the anions alone be capable of movement. First one, first anion it will start movement, alone movement takes place. Next, cation is also start. Next, second one, let the anions and cations move at the same. Okay, anions also it will move one side, cation also it will move in another side. Okay, let the anion and cation move at the same. Next, the third case, let the cations move at twice the speed of the anion. Cation movement is faster, cation move at twice the speed of anion. So these are the observation in the transport number we are going to observe. Okay, we are observing these type of three variations in the electrolyte, in the solutions. Okay, so next, based on this principle, based on this concept, we are going to determine or discuss determination of transport number by Hittrof's method. What is this determination of transport number by Hittrof's method? Here you see, this is the principle. During the electrolysis, the fall of concentration around the electrode is proportional to the speed of ions moving away from the electrodes. Okay, the principle of Hittrof method, during the electrolysis, the fall of concentration around the electrode is proportional to the speed of ion moving away from the electrode. Just you understand the concept. Okay, what is that? Electrolysis process is going on in the electrolytic or a cell. The concentration is fall. Why? Because the variation taking place. Ions attracted towards the oppositely charged electrode. Okay, then the concentration variation takes place. This is proportional to the speed of ions moving away from the electrodes. So this is depends on is proportional to the speed of ions moving away from the electrode. This is the principle. Thus, the fall of concentration around the cathode is directly proportional to, he explained, the thus the fall of concentration around the cathode is directly proportional to the speed of an ion. So first, because oppositely charged, cathode negative, it attracts, and cathode here one charge, it attracts another one, anion. Okay, UA. Then next one, here the fall of concentration around the cathode is directly proportional to speed of anion UA. This is equation number 1. Or loss or fall of concentration around anode is directly proportional to speed of cation. We are representing UC. One is UA, anion, mobility of anion. Then cation is UC. So this is equation number 1. This is equation number 2. Dividing equation 1 by 2. Dividing equation 1 by 2. I will write like this. What he said? Fall of concentration around cathode UA divided by fall of concentration around anode UC. I written like this. Next, add 1 on both sides. I will going to add 1. Okay. So 1 plus fall of concentration around cathode divided by fall of concentration around anode is equal to 1 plus UA divided by UC. Here I will going to take LCM. Fall of concentration around anode plus fall of concentration around cathode divided by fall of concentration around anode. I written like this. Here UC plus, what is that UC? Anode plus cathode UA divided by UC. So this anode and cathode both are there, no? So that's why I written like this. This fall of concentration anode plus fall of concentration around cathode. So these two I will written like this. Total fall of concentration divided by fall of concentration around anode is equal to, what are the things are there here? UC plus UA. Why? Because total fall of concentration UC plus UA divided by UC. Next, taking reciprocal, this equation I will going to take the reciprocal. Then reciprocal is nothing but what? Reverse. Okay, denominator to denominator, numerator. So what? Fall of concentration around the anode divided by total fall of concentration. Here this is reverse. UC divided by UC plus UA. We know that. What is that? The previous explanation in the transport number representation. T plus is equal to UC divided by UC plus UA. So we know the concept of this transport number of cation, transport number of anion. Similarly, with the help of this, we know the concept. With the help of representation, we will written like this. Fall of concentration around the anode divided by these things. Instead of these, I written like this here. T plus, instead of UC divided by UC plus UA, I written like this. Yes. Similarly, fall of concentration around cathode divided by total fall of concentration is equal to T minus. Okay. So this is the representation of Hittrof's number. You know the mechanism of Hittrof number. Now I will go to give one better example how to find out the transport number. So using the Hittrof method. All of you getting the concept of this? Any doubt? Any doubt? All of you getting or not? This explanation?
No doubt, sir.
Okay, fine. The next. Okay. After this, we know the mechanism, Hittrof's mechanism. Equally, first alone, anion alone, it will move, attract to the cathode. After that, cathode is cation is moving. Then similar number of ions discharge, but the center compartment, middle compartment, there is no variation. There is no variation in the concentration. It is equilibrium established. It will stand as it is. So here, just you see, how you going to determine this transport number with the help of Hittrof's method? The operators used for the determination of transport number of Hittrof's method is shown below. Just you see this. This is the operators. Okay. Electrodes are there, anode and then cathode compartment. Then here you see center compartment, middle compartment. This is okay. Then stopcock is also there. Stopcock here knobs also there. Next here you see externally the silver anode, this silver anode limbs externally connected to the resistance. Next here platinum cathode externally connected to the battery present in the silver voltmeter. This is the cathode limb. Next, this is the negative sign. The ammeter is there. It will measure the current flow of current. Next, here the center a U-shaped tube is there. In this U-shaped tube, stopcock is there. This is S1 and then S2, and then in the anode compartment, anode limb, here S3 knob is also there. S3 knob. What are the uses? I will tell you. What are the use of this knob? I will tell you in the discussion. So these are the operators we are going to use in this experiment. Okay. Here, let 1 Faraday of current passed through the cell. What type of variation taking place? Just you see, we are pass 1 Faraday of charge into the cell or this setup. What are the variation? Just you see this. This is only for your understanding purpose. Okay. Anode compartment, cathode compartment, middle compartment. So this is the middle compartment. Here, no concentration change in the middle compartment. Anode compartment, loss T minus 1 minus T minus ion, it varies. Here what happened? Here net loss of 1 minus T plus ion it loses. Okay. So 1 mole of M plus discharge. Here 1 mole of A minus anion is discharged here. So these are the general discussion only for your understanding purpose. This is the operators, actual operators. What is the use of these operators? How we can use these operators? I will tell you now. Working principle. Here, this method is based on the principle that the concentration changes occur around the electrodes due to the migration of ions. So this is the principle. So movement of ions, then the variation of the charges or a concentration in the solution or the two compartment. This method is based on the principle that the concentration changes occur around the electrodes due to the migration of ions. Okay, is explained this principle. Yeah. After this, the apparatus used consists of U-shaped tube connected on one side to the anode limb. Already you know what is that anode limb. I already showed limb, and on the other side to the cathode limb. The anode is made of silver and cathode is made of platinum metal. The U-tube, the anode limb and cathode limb are filled with the standard solution of AgNO3. Here we are going to determine Ag. So that's why we are using standard solution is we know the concentration of the AgNO3 solution. So that's why standard solution of AgNO3 we are using in the central limb. Next, anode and then cathode limb. The apparatus is connected in series to a silver voltmeter. Just you see, this is the silver voltmeter. We are connected like this, series connection. Okay. So next, here a steady current of about 0.01 ampere is passed for about 2 to 3 hours. We are going to pass 1.01 ampere current into this setup. Okay. So what happened after that? The stopcock X1 and S2. Just you see this stopcock S1 and then S2. Stopcock S1 and S2 are closed. So why? Just you see here, we are going to pass the current here. Current is passes, the movement taking place, okay, the mobility is taking place up to 3 hours continuously. After 3 hours, you here you close this stop clock S1 and then S2. Next, the whole of the solution from anode limb is taken out, through stop clock S2. The solution, anode limb, what are the solutions are there? Taken out from the S3 stop clock. So, here S3 in a weighed flask. The silver content of this solution is determined by Euler's method. So, we are going to weigh the silver content, contamination, what are the silver contamination present. So, we are going to measure this one, Euler's method here. The weight of silver deposited in the silver voltmeter is also determined. Okay, so what the weight of silver deposited in the silver voltmeter is also determined. So here the complete setup, the work is very simple. You take standard AgNO3 solution, you fill both the compartment, electrode, anode limb and then cathode limb, and then 0.01 ampere current pass up to 2 to 3 hours continuously. Next, you close the stop cock S1 and then S2. Then, what are the solutions or AgNO3 present in the anode limb? You take it out from the anode limb through S3. Next, you determine that anode, what are the AgNO3 concentration present, the content of the solution determined by Euler's method, that is different. Next, the weight of silver deposited in the silver voltmeter. Where is that silver voltmeter? Here you see silver voltmeter is also contains some amount of silver. Okay, you go and determine, that is the Hittrof's method. Okay, silver voltmeter is also determined. Next, here observation and calculation. Mass of silver deposited in silver voltmeter. So first, before fixing that silver voltmeter, you weigh the accurate weight of the original one. After completion of this experiment, you take the, after that, okay, after completion of this experiment, after 2 to 3 hours, you measure once again, that's voltmeter. Okay, next, this mass W is proportional to the total current pass. Mass of the solution taken out from the anode limb. Mass of AgNO3 in a gram of the solution. Generally, we are taking that one B grams. Mass of water in the solution A minus B grams. Next, mass of AgNO3 associated with A minus B gram of water before electrolysis. Standard solution of AgNO3, that is called a C gram. Increase in mass of AgNO3 around anode, increase in weight of AgNO3 around anode after electrolysis, B minus C gram. Then formula, we are going to take this formula weight of AgNO3, 108 plus 14 plus 48. What is that? 16 into 3. Okay. Next, 14 nitrogen, Ag. So these are all the weight of the AgNO3. You are going to take this standard formula. Next, you calculate. Therefore, 170 gram of AgNO3 is equal to 108 gram of Ag. So this is the calculation of Ag. 1 gram of AgNO3 is equal to how much of Ag present? Here 108 divided by 170. You will get the answer. Okay. So 1 gram of AgNO3 containing how much of Ag? So B minus C gram of AgNO3 is equal to 108 divided by 170. This is the standard equation. Okay, standard equation 108 divided by 170 into B minus A. What is this B minus A? We know B minus C. Sorry, B minus C. We know here before doing the experiment, you note down the weight. Then after completion of the experiment, you take the weight of the what is that? What we are going to use, adsorbed electrodes. Okay, in the experimental setup, B minus C is equal to X gram. Next, thus increase in mass of silver around after electrolysis, that how much? X gram. If the silver ions Ag plus had not migrated from anode, then the the increase in mass of silver would have been W gram. Hence, decrease in the concentration around anode as a result of migration of Ag plus ions will be W minus X. W minus X is nothing but what? What is the W? Here you see mass of silver deposited in silver voltmeter. So how much silver deposited in the silver voltmeter? That then finally what are getting? How much silver present in 1 gram? What we are calculating in the last? That W minus X. W is always so W minus X divided by W. So here you see W gram, hence decrease in the concentration around the anode as a result of migration of Ag plus ion will be W minus X gram. This decrease will be proportional to the speed of Ag plus ions, because already we know, okay, why? Because the positive ion movement is twice greater than the negative ion. So that's why cations and then anions, and the speed is proportional to the fraction of current carried by Ag plus ion. Therefore, transport number of Ag plus ions, TAg plus, is given by, we are going to calculate like this. TAg plus is equal to fall in concentration around anode divided by total current passed. Total current passed here W, that is W, here W minus X. In AgNO3 solution, we have AgNO3 solutions, we have T and then T plus T minus are there. Ag after electrolysis of AgNO3 after electrolysis, we getting Ag plus NO3 minus. So you substitute like this. Ag instead of plus, Ag plus you write Ag TAg plus TNO3 minus is equal to 1. Therefore, TNO3 minus is equal to 1 minus TAg plus. So this is the equation. Next, what are the things are there here? TAg plus is equal to W minus X divided by W, no? So here is equal to 1 minus, here you see 1 minus, instead of this TAg plus you substitute this 1 minus W minus X divided by W. Here or TNO3 minus the negative sign here is equal to 1 minus W minus X divided by W. So we getting, then we are going to calculate this. Thus, the transport number of Ag plus and NO3 ion, NO3 minus ion in the standard solution of AgNO3 can be calculated like this. So similarly, we are going to calculate the transport number by using Hittrof's method. Okay, so once again I will going to repeat this. Any doubt about this point, guys? Are you getting all the points
Yes, sir.
clearly?
Yes, sir.
Okay, once again we'll repeat this, the experimental part, only experimental part. Okay, what are the things are there here? Here you see, this is the operators. Okay, this operator is there, Hittrof's operators. This is Hittrof's operator to determine the transport number. Here 3 chambers compartments, already I discussed in the theory. 3 compartment, anode compartment, cathode compartment, then middle compartment. 3 compartment are there. Then you connect like this externally in series in silver voltmeter. Next, here 3 knobs are there. Knobs means cork, okay, stop cork, or knob, generally we are also called knobs. Okay, S1, S2 and then S3. Here, this diagram, you see this anode and then cathode, you should fill standard AgNO3 solution. Completely you fill standard AgNO3 solution. Next, you pass 0.01 ampere for 3 hours. You continuously pass this. Then what happen? It will movement or moving takes place. Mobility of ion takes place from anode to cathode. Movement taking place. After 3 hours, you stop the cork S1 and then S2. You close the knob S1 and then S2. Next, what you do? That anode limbs solutions present, you take that solution through S3 knob, you collect, and then you measure the concentration or deposited silver present in the in anode limbs. Then after this, in the silver voltmeter is there. Before doing this experiment or conducting this experiment, you measure the electrodes here in the voltmeter. After completion of the experiment, you take once again that weight. You will get the accurate weight or deposited silver getting after completion of your experiment. You take that one as first one A and then B, or C minus B, okay, or B minus C you will get. So with the help of that B minus C value, you will get X value. With the help of that X value, finally you calculate the transport number. You see, that one only discussed. This method is based on the principle of the concentration changes occur around the electrodes due to the migration of ions. The apparatus used consists of a U-shaped tube connected on one side to the anode limb, and on the other side is the cathode limb. The anode is made of silver and cathode is made of platinum metal. U2, the anode limb and cathode limb is filled with standard solution of AgNO3. The apparatus is connected in series to a silver voltmeter. Next, the steady current of about 0.01 ampere is passed about 2 to 3 hours. After that, the stopcock S1 and S2 are closed. Okay. Next, what happened? The whole of the solution from the anode limb is taken out through the stopcock 3 S3 in a weighed flask. Okay, you weigh that. The silver content of this solution is determined by Euler's method. You can weigh that one and then you determine how much silver content is there in the solution. Next, what you are going to do in the Hittrof method? You take the weight of silver deposited in the silver voltmeter in solution determined. Okay, so this is the observation part. With the help of this observation, you substitute all the things, what are the value getting from the experiment. Next, the standard equation of AgNO3, 108 plus 14 plus 48, 170. So therefore, AgNO3, 170 gram of AgNO3 is equal to 108 gram of Ag. Ag is 108 in 1 gram. Okay, 170 gram of AgNO3 is equal to 108 gram of Ag. In this, 1 gram of Ag is equal to 108 divided by 170. You will get the value, accurate value present in the or deposited Ag in the voltmeter. B minus C gram of AgNO3 is equal to 108 divided by 170 into B minus C is equal to X gram. So this is the calculation of transport number. TAg plus fall in concentration around anode divided by total current passed is equal to W minus X. We get the value in the observation column. W value we know, X value we know. With the help of this W minus X divided by W, you calculate this. T plus T minus is equal to 1. We know the transport number, the equation. T plus T minus is equal to 1. You substitute this. T plus in this in plus, replace that. Ag plus you write. T Ag plus T NO3 minus is equal to 1. You substitute this, you substitute all the value, you can easily find out T Ag plus value and T NO3 minus value, all the things. Thus the transport number of Ag plus and NO3 minus in the standard solution of AgNO3 can be calculated. So this is the relative speed of ions during electrolysis. Once again, just this is the representation, the movement of or mobility of ions and the cathode and anode compartment. Okay, so now you tell me any doubts about this, anything else. 1 second, I will tell you. Tell me anything. Are you getting all the things or not?